Okay, that we covered already. You've seen this video already, right? Remember? What is this? By cameras. Okay. Let's see if that everybody agrees with that. Okay. So I'm going to just play this video. You've already seen this video. Okay. So towards the end, I'm going to ask some questions. Okay. All right.
To be obligated with this arm, it proves to be sufficient safety and effectiveness to warrant this market and allow someone to take the critical water, something that people can't do. So the potential impact to subvert basic human functions that make those who are affected by these disorders feel like normal people is remarkable to consider. Now, here's the interesting part. The engineer operating arm actually makes a mistake here. Say they wrench drops, and yet the device has enough dexterity to get the prosthetic hand back onto the wrench and pick up the object and perform the function. Now, I'm not suggesting that wrench maneuvering is the critical task that people who are paralyzed need, but it shows the degree of control that this arm prototype has at this point. Now, remember, this is a prototype, and there's still a component of studies that include placing the sensor on the surface of the brain and performing the clinical trials to provide reasonable assurance that that's a safe and effective approach before this thing gets market. But the timeline that Jonathan proposed is tends to be pretty aggressive.
Okay, so how is the hand being controlled? Huh? What is it? Is it just say? Did I hear camera? Camera. Okay. Okay, anybody else? How was the hand being controlled? He also said camera. Glove, right? So he was, remember this? So in the part one we discussed, so he was wearing a glove. And that glove is instrumented, it has sensors. So when the hand moves, right, the glove moves along with the hand, and he's able to control, with those signals, he's able to control the hand part of the arm. What about the arm? Shoulder, elbow, wrist joints. How are those being controlled? Huh? Right, right. Accelerometers and IMU sensors were at these three different locations. They were controlling the arm movements. Make sense? Okay. They have 6 degrees of freedom XYZ and yaw pitch roll, each sensor. So they were giving that indication for the 3 joints. Yes? Yes? Everyone understood that? Okay. All right. Anything else that you got from that video? Useless? Huh? Anything else that you got from that video? So let's say, so the way they demonstrated it, right? The way they demonstrated it, if somebody has to use the arm like that, what should they have? They should have their hand working. if they have their hand working? Do they need a prosthetic? So then what was the point? Very good. Very good. Yes. So telerobotics, right? So let's say I want to move something in my office that is in Maryland, Baltimore, but I'm here. Okay. And I have robots sitting there that can do my work, turn on lights on and off so students think that I'm there, right? Yeah. So I could do that using robots, but they're controlled by sensors from here. Yeah. Okay, good. Um, and then in the video, he was very focusing on some of the activities. So what is ADL? What does ADL stand for? Activities of daily living, ADL, right? And then we also talked about something else, IAD. What is that? Very good. Very good. Wow. Okay. You guys are learning something from this, right? Right? Other than Rajnikant. We're learning something. Okay, good, good, good. Okay, so you see how he was focusing on using these limbs for activities of daily living, right? So the purpose, right? So, and that's why they designed that test where they're trying to show these very, very detailed movement, right? Holding a clippers, right? Holding a delicate thing and then moving it. See that movement, right? Can you all just do that movement now with your hands? Just do that movement. Think that you're holding a clipper, lift it, move it, right? See how easily you're doing it, right? Right? It's so easy. And if you want to replicate the same thing in a robotic hand, you see how many mistakes he did and that he had to cover up in the video that, hey, he made a mistake voluntarily. He said that, right? Did you see that, right? I mean, and then he drops, the hand goes back. You see how difficult it is. That is exactly how it will be when a physiotherapist is working with a paralyzed hand. It is like a robotic hand, huh? A robotic hand, but now more layers to it. Ma'am was sharing in the break. There's stiffness, there's clenched fist. The hand is like this. It's not even like robotic hand is like this, and you can start using it with a joystick, right? So it's like this, and they had to get it back, right? So it's that difficult, right? So control. Control is really important, right? And then on top of it, controlling with limited biosignals. That adds another layer of complexity. Okay? All right. So now that we have seen upper limb, what are we going to do next? Lower limb. Yes. Okay. Yeah, like I said, right? No negative points, no silver coins. Take guesses, no problems. Yeah, yeah. Okay. So lower limb amputations, we have disarticulations at the joints. So we have hip disarticulation, we have knee disarticulation. Okay, and then we also have transfemoral, that is above knee, and transtibial, that is below knee. So these are different types of amputations, and for these, there are different types of prostheses, right? Transtibial, that is below knee, and transfemoral, that is above knee, and you can see different types of prostheses. So um, I think you made a point that I think you both made a point that aesthetics in prosthetics, right? So this is one video we're going to look at it, and let's watch this video carefully, okay? And again, I'm going to ask a lot of questions, okay? Is this fun? Is this good? Yes? Okay? All right, let's do this. Okay.
She said, I trying to like, so she became first NCAA track team. She says, with the records in 1996 Paralympics, she made headlines. Something effective. Disabled people run faster than me. I'm not, well then, how disabled am I? She found her voice and began to laugh. After all, only she can decide how tall she's going to be today. How did you decide how tall you want to be? It's a good and she told us the secret is to surround yourself with people wish you to say yes. Yes to a commercial for L'Oreal. There's only one thing that you kind of written. Yes to the opportunity to walk the runway of Alexander McQueen fashion show on artificial legs with 6-inch heels. It's just even thinking about it now, my adrenaline's pumping. I thought, don't think about the consequences of where everyone's going to think you fall. Just get to be the not bad advice provided. I think that the reaction and response I've had from so many people. Not to say about my prosthetic legs, but if you know what it's like to feel that they're not normal, feel that they're different, that they're different, is that you so, with strength to everyone, it's encouraged to be the other. If you hand somebody a key to their own power, if you feel so respected, you're teaching them to open doors that they want. Thank you. So we choose a knowledge. We also about learning to God. I only said one word because the words are come, let us dance.
All right. How was that? Powerful, right? Very inspiring. Okay, what are some of the learning lessons from that? What did you notice? She was giving a, sorry? Right, right. She didn't give up. Never give up is a good message, yes. Yeah. Huh? Yeah. Powerfully in her own way. Yes, message, okay? Okay. Anything? Lower limb prosthetic. Thank you. Good observation, yes. Lower limb prosthetics. And then when she was walking on the runway, you saw those prosthetics? Aesthetics in prosthetics, yes. And for the males in the room, I don't think we have any experience wearing 6-inch heels, right? And I'm sure some females in the room, I'm sure they have tried that, right? That itself, for healthy people, that itself is a challenge, right? Right, and on top of it, she was wearing 6-inch heels, right? So that's, okay, all right. Anything else? She was giving a TED Talk. How many of you watch TED Talks here? Please write that down. Please write that down. Watch, instead of TikTok, let's watch TED Talks. Make that a practice. 5 minutes a day, okay? Give that promise to me, yeah? TED Talks, TED, right? Let's do that. Okay, this is BMW sponsored TED Talks. These are amazing. These are life-changing, okay? All right, so please watch a video, 5 minutes, yeah? All right, okay. When she was giving a TED Talk, she said something. Okay, did you guys notice? Did anyone notice? Right, very good. Okay. Very good memory also. You know, you almost repeated the sentence. Very good. But she also right before that, she said something. People called her. Huh? Well, valueless, eh? What? Okay. So you know, disabled, crippled, senile. She used those words, remember? So this was my first grant proposal that I was writing. So I wrote, this technology will help paralyzed. And I said paralyzed people. Is there anything wrong with that? Is there any grammar mistake in that? Paralyzed people, paralyzed. This technology will help with exactly. They rejected my grant. I got 9.5 out of 10 score. They rejected my grant. And the reviewer, in the summary, the first statement he said was, stop using the victim language. You should address them as individuals with disabilities. Right? Right. So that was my first grant experience. And I was, although they rejected, I was so happy to learn that lesson in my life. Individuals with disabilities, they are individuals. You can't just label them as paralyzed from that day when they got the stroke. I got connected, that registered in my head after my mom had paralysis. Okay. So she's my mom. She's a person. She's not paralyzed, right? I cannot address her like that. Individual with disabilities, individuals with paralysis, individual with movement disorders. Okay. This is an important lesson for you all. Okay. When you're handicapped, individual with handicap, right? Individual with disabilities. This is really, really important. Language. Somebody will pick your proposal that you're writing, a fellowship application, a statement of purpose that you're writing. Somebody will pick on it, and they might reject you. That you will lose 1 year, right? Right? And just not because you might lose 1 year, but do the things in the right way, right? Respect them, right? You can't identify somebody with their handicap. You can't identify somebody with their disability. This is such an important lesson. Yes? Everybody agrees? Yeah? Right? Very good. Okay. All right. Anything else from that video? The closing message was that Persian god who said, what? Oh, yes, yes. Ah, okay. Very good. Okay. Thank you for sharing that. All right. The closing message was that Persian god who said, what? What? Who said that? Yeah. Can you say that loud? Come, let us dance. Okay. So that was my first message in part one, right? Dance once in a while. It's okay. Yeah. All right. Okay. So we saw some upper limb prosthetics as well as some lower limb prosthetics, right? We saw some upper limb prosthetics as well as lower limb prosthetics. What are some of the differences that you noticed in so far what you saw? Lower limb. Lower limb was complicated. Lower limb was complicated. Okay. Okay, but you felt that lower limb was complicated. No, I'm just asking. You felt that. That's okay. Okay. All right. Any other answers? Mm-mm-mm. Right. Right. Yes. Right. So movements are different, upper limb, lower limb. Yes. Yeah. Huh? Uh-huh. Uh-huh. Oh, okay. Is it difficult? Yes. Okay. Yeah, that's right. That is right. Okay. Okay. Very good. Very good. Everybody following those comments, observations? Yes. Okay. Uh-huh. Yeah. Yes. Okay. Very good. So that was one point I was trying to hit on, right? So, but the upper limb prosthetics also complicated in their own way. They had a lot of components, a lot of motors, right? You saw that, right? Upper limb prosthetics, they had a lot of components, motors, they were electrically powered, right? And lower limb prosthetics, they were they were mechanical, they didn't use any power, right? Right? So that's what you saw so far, right? And everybody, I really like the answers that you guys gave. Is that lower limb prostheses, what is their function? Balance and stability, right? So they were providing that. They might look simple, but they were providing an important feature of the prosthetic is that stability and posture, right? But then the other difference was that all the lower limb prostheses that you saw so far are passive prostheses, not actively powered by electrical motors, etc. So we'll see that in just a second. But before we go there, I want you all to do an exercise, okay? So we will all stand up, okay? Stand up, but you will spread your hands like this, okay? So have enough space. You'll stand up and you will spread your hands like that. Then we're going to close our eyes, okay? Close our eyes and I'm going to count till 20. Put your head, okay? Okay? And what you're going to do is observe yourself. Observe yourself. Just like mindfulness, okay? Just focus on yourself. Okay? Focus on the body, focus on the posture. Okay? That's all what we're doing, this exercise. Got it? Yes? Ready? Okay? So spread your hands, close your eyes, and I'm counting, okay? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 19, 19, 20. Okay, let's stop, let's relax, put your hands down, open your eyes. Okay, good. Good. Okay. All right. Okay. So my question to you, we're done. Okay. Okay. Settle down. Settle down. Okay. So what did you observe?
Like, I'm not. Like, excited, really got.
Okay, good. So he's getting. Did everybody hear me? Bangalore. So sir is sharing that it felt like he was almost about to fall. And sir, you same. Both of you are about to fall. Huh? Oh, arms felt heavy. Okay. You should work out. You're not even holding any weights, and you're still okay. No, that to hold like this for the tests. Okay. Anything else? Arms. See a doctor. See if it's. I'm so sorry. It was funny. Okay. Yeah, I was like, back is paining. What do man can't. That's funny. Okay. What else? That's hurting me now. The laugh. Okay. What else? Okay. You had difficulty like holding the posture. You should have fell on her, then pain me. Okay. So any other answers from this side? What was your experience other than you taking pictures when we were all doing that? Pain. You also felt pain and fatigue at this age. Okay. Okay. So going back to that, so both of them, they felt they were almost about to fall. You had difficulty holding the posture, right? So when you were standing like this, okay, your eyes were closed. So you missed an important demo. Um, so your eyes were closed, you're standing like this. Believe it or not, we don't have sensors to measure, but you were doing this. This is your body, right? So you're standing like this, eyes closed, you were doing this. You're swinging back and forth. How much we swing depends on the age, right? How much we swing depends on the age. And at some age, you might as well. Hopefully not, but yeah. So you're really holding the posture, but you're swinging back and forth, right? You're swinging back and forth. And in order to maintain that postural stability, we use different strategies. We don't even know that we're using, but we use these strategies. We have hip, knee, and ankle strategies. These three joints, they're bending and they're trying to nicely balance you. You see this? You don't even notice that. You see those balloon characters that are like, it is like that. It is exactly like that. Okay. So when how many of you have studied movement biomechanics? Right, sir? Yeah. So of course, when you study human postural control, um, you design human postural control as an inverted pendulum. Okay. Pendulum, right? Easy. Inverted pendulum. Inverted pendulum. Has anybody tried to balance an inverted pendulum? It is very, you've tried. Okay. It is very difficult or easy for you? Difficult, yes. Right? Inverted pendulum. It is very difficult to balance. That is exactly what we are doing every day. Then how is that we're so good at it? Huh? The controller is good. The controller is good because we have trained it over the years. We fell. When we were kids, we fell. Right? And we have learned over the years to stabilize, right? But that same controller, when it has lesions, right, cerebral lesions, etc., when we get into disease, then that same controller gives problems. That's why we need to study these. Falls, Parkinson's disease. Sir, you were doing Parkinson's disease, freeze of gait, and postural stability is some of the major concerns for Parkinson's disease. Yeah. Okay. So far what you saw are passive lower limb prostheses, but they're also active lower limb prostheses. And this is one video. And again, I'm gonna ask some questions after the video. Okay? Yes? Ready? Ready for more? Okay.
I was 16 years old, he went over there, heard the yellow, bed and saw something take me under, he saw the back end of the shark, and there's so much tissue down there, and it's kind of the flesh going on, and it was irreparable.
2 years later, engaged for a challenge, Hutto became the first test pilot for a unique and powerful new prosthetic leg developed by mechanical engineer Michael Goldfarb and his team at Vanderbilt University. The effort was kickstarted by a grant from the National Science Foundation. Able to develop a early prototype that demonstrated it could have a leg that was wide enough and clear sort of the biomechanical levels of torque and power. Version 1.0 evolved into a more streamlined 2.0. Computer controlled with advanced range of motion in the joints. This is the battery, the power and everything. You have a motor here that drives the knee joint, motor here that drives the ankle joint. This is the whole computer board that essentially tells the motor to do the joints.
To have the computing capability on board to work synergistically with the user to provide the torque and the wrench.
It's designed to respond to cues from the wearer.
Right before I go to Sarah's in, I kind of kick my thigh back just a little bit, and just that little movement tells it, hey, you're about to walk upstairs.
To reduce the risk of injury, Goldfarb's team has intentionally programmed a slight delay into the leg's computer. Hutto confirms it takes less effort to walk compared to the prosthetic he wears on a daily basis.
With my leg, it is hard because it's always a step behind me.
Goldfarb says in the years of work, they have sold their technology to a major prosthetic manufacturer. And no relative is really, if these are going to really gain large value. And Hutto, who is now studying to be a nurse, is looking forward to one day soon walking tall on a bionic leg that he helped make a reality. For Science Nation, I'm Miles O'Brien.
All right. How was that? Good, good. Okay. From the video, what did you observe? Right, right. Very good. Yes. Right. Very good point. So they tested all the terrains, right? So that is one of the part of testing, right? You can't just design something that will be for the right, right. Very good. Okay. Okay. What else? Sorry. Two motors were controlling. Yes. Yeah. And did you notice about the cues? Right? Did you notice about the cues? What were they? How was the person signaling? Right, right. You saw that, right? So he was doing that, and he was doing that, right? Just to tell that now I'm going to switch more to stairs, right? Yeah. So that is one way he was conveying, right? So you could use those cues, those sensors to switch modes. Yeah. Okay. And what else? He said that. So let's show you the way you're walking, right? The way you're walking. Both of your legs are trying to catch up, right? But suddenly when you have a prosthetic, then you drag, right? See, he commented about that, right? So if he has a plastic prosthetic, it's kind of dragging, right? So it is always one step behind. But this active prosthetic was catching up. So that reduces a lot of effort on him. Okay? This is some of the important design consideration that they silently slipped into these videos, sharing their experiences. Yeah. Okay. Anything else that you saw that was really cool? The virtual reality simulators. Did you notice that? Right. So if you have to buy a prosthetic like that, right, it will cost you some 100K, 50K USD, right? It is expensive, right? It is expensive for everybody. It is expensive. But that virtual reality simulator, that will cost zero rupees, $0. Zero is the same everywhere, right? Right? That virtual reality you can use, right? It's Unity 3D. It is free. Virtual reality models, they are free, right? For all your undergraduate, whatever projects, you can start there, right? Yeah. Such a easy, low cost environment for us to test things. Yeah. And not only just testing, but you can also use physics engines in those virtual reality simulators, right? So you can actually simulate physics. It is actually like real exoskeleton, right? Real robot that you're trained. Okay. So now we have a 5-minute exercise for you. Okay. So each row you're sitting, that's a team. Okay. All right. So that is a team. So you are going to talk to each other now. Okay. For 10 minutes. Okay. So we have 12:33. Okay. Talk to each other, not about Robot 2 and Rajnikant. Okay. So I'm going to give you exercise. Wait. Okay. It's 12:33. So we'll do it for 10 minutes. Okay. This is the question that we're trying to answer. What can we use? What signals can we use? Write them down on the paper so I can come by and see. Okay. All right. What signals can we use to control prosthetic? Try to think something really out of the box, okay? Really out of the box. So something nobody has thought about. And start writing so I can see that you're progressing and you're doing something. Okay. Start writing. Okay. It's the time. Okay, we have 3 more minutes. Okay, 3 more minutes. End of scientific discovery. Okay. 3 more minutes. Please try to wrap up. Try to come up with your answers. Okay, so wait. Everybody, one quick announcement. So when I start asking, so we'll go by each row, and when I start asking, I want one answer from each table. Okay, one answer, and that will be your top candidate, top answer. Okay, because I saw in all your notebooks, I saw at least 6 or 7, right? Right. I want one top. Okay, the best candidate from it. Okay. Right. Oh. Like I said, think out of the box. It could be anything. Okay, that's how you come with new ideas. Don't go again EMGs. We've seen those. Okay, try something new. Okay. Okay, so we're getting closer. We're getting closer. So um, each team, now choose one person who will be speaking. Okay, choose a spokesperson. Okay, one person, each team. Ready? Are we ready? Yes. Okay, please settle down. All right. All right, we're done. We're done with the exercise. We're done with the exercise. The last team, okay, settle down. So we'll start. I want every other team to hear to every team, right? Right? So we need to hear them. So they worked hard and they have come up with a technology that doesn't leak. Okay. All right. Let's start. Let's start with you guys. One. Yeah, actually, can I get them? And I need a volunteer. So you one technology.
Yes, sir. Our idea is to use,
One.
yeah,
One word.
to use the motor imagery, bilateral.
Bilateral.
Yeah,
What is the signal?
signal will be no.
EEG.
Yeah, EEG, exactly. Yeah. If one leg is amputated, using the other leg, the data we need to sync and
Oh, okay. Contralateral.
yes,
Ipsilateral. Okay. Ipsilateral imagery. So bilateral motor imagery, EEG. EEG. Okay. Let's give a round of applause to this team, please. Okay, in your team, who's the focus?
Sir, with pattern recognition, with the use of sensors and AML, we can detect those advanced myoelectric movements, and we can EMG. It's not. No, it is more advanced because pattern with AML, if the pattern was insisted to it, and it get recognized word. What is the signal? EMG. Yes, sir. Yes, sir, it is EMG only.
But pattern recognition. Yeah, you got it. Got it. Okay, next up. Can you pass the mic, please?
Sir, so our idea is to have a technology which can recognize synapses. So for instance, model. So if he does not have his upper limb, so we could like connect a prosthetic which could have a technology to like recognize the impulses from brain, electrical impulses
Oh,
by synapses recognition.
oh.
EEG.
Yeah.
But not exactly EEG. We could have other technologies like proximal predictivity. Like for
Please,
instance,
everybody, please calm down. Let's start.
for instance, if he loses an upper limb, there are not going to be a lot of actions that like would help him on a regular basis. It's going to be basic actions. For instance, to like clasp his hand or like to open the door and all that, or to write. So as you said yesterday, there are only two motions which help us do like 90% of our actions. So for instance, if we already pre-program it using a technology, maybe if like he get a synapses to like raise his hand, it's most probably the next action will be to clasp it. So we could develop a technology like that. Yeah, like a neurochip, but that's a very advanced option. Sir. So it's for it.
Synapse.
Hmm.
We call it. Okay. EEG. But the synapse is what they're saying.
Why is it? Why?
Pass back, please.
Why
Thank
is
you.
it?
Please don't beat him like that.
So intention decoding, sir.
Intention.
Decoding.
How?
So using the EMG signals, sir.
EMG.
Before actual movement happens, our brain sends the muscles the very weak signals, sir.
So what EMG?
EMG signals
Where?
from a brain, sir.
From where?
The place of prosthetic where we use, sir. Like if you're using a prosthetic in our hands, the electrodes will be placed near our fingers or near the wrist, where we actually. Before a movement could happen, for example, if I have to move my hand, my brain will be sending signals to my hand, right? Sir? So initially a weak signal will be sent before the actual movement. So we are predicting the weak signal before the movement happens, and we are predicting the movement as well, sir.
Okay, intention.
Intention decoding. Sir. Yes, sir.
Please write intention EMG. Synapse was the third. Synapse. That's why I named it.
By using ultrasounds, by using ultrasounds, yes, sir, by collecting the information, electrical activities from the muscles. When we flex our muscles, it will give some electrical activities that ultrasound will detect it, and it will give, move the process.
No. Ultrasound, impossible.
Oh.
Intention EMG was the number. Intention decoding using EMG.
Okay, now.
Intention, not intense.
Oh, okay.
Intention. We're not going to do a spell check, don't worry. Intention EMG. I'll write one or two, then you can appreciate how good you are. Intention EMG. Ultrasound, EMG, EMG, ultrasound. Okay, good. Thanks.
So I'm thinking about the brain chip, like we will put the chip in the brain and we will integrate it with AI. So the AI will bridge the gap between the signals of neurons, which are called as motor cortex, and it will be bridging the gap and it will be directly connected to the machines. And after that, if it is making the complexions, then we will be working on the predictions.
Great signals, but invasive.
Yeah,
The chip.
yeah. Put a chip and
What's it?
we'll just do surgery.
Invasive.
Yeah, surgery. Yeah.
Okay, all right, well, thank you so much.
Yeah.
Brain chip invasive. Invasive, right?
Yes, with AI.
See what's going on. Okay, so. An answer. I come back to you. I need an answer. I want to go back and work with your team, but I need an answer. Okay. Okay.
So sensor-based smart card.
Uh-huh.
Object crushing.
Okay. No, but what is the sensor base? Sensor, what sensors? Accelerometer. Okay, accelerometer sensor. Thank you. Sensor based to avoid
Object crushing.
object crushing. Okay, yes.
The same
How do you-
smart object.
How do you do that? Hold.
That and all I need to do research.
Thank you so much. No worries. You did good. Very good. Let's clap. No, we didn't. The chip team. All right. Okay. Was
I think pre-processing is the idea to control prosthetic device.
all the time.
But definitely we are design a filter so that we can control the outputs.
Pre-processing, filtering, for all of it. Right? Any of these signals.
Yes.
We will do pre-processing and filtering.
Yes. Then so that's why, in my opinion, that's in our team we work on filter designs also, mainly filter designs. Designs.
So much, yeah. Let's clap. Let's clap. Okay. Is there so what way the best you install it? Okay.
We are slightly agree with the other team. We are using the brain signals with a non-invasive method. That means we need to identify the nerve endings at the stump. So we can sense the action potential is originating from the brain. So yeah, stump. So the nerve endings giving the action potential. So the sensor can receive. So that can activate the appropriate action.
Don't talk, please.
So through that we can control the process.
Very good. Thank you so much. Nerve endings, nerve from the stump. Nerve from the stump. Yeah. Okay. Very good. Thanks, sir. Thank you. This team. Yeah, we did clap. Hey, your team. Who's this spokesman?
So simple. Something so simple. We can. There is an app called Modular where we can command the prosthesis to adjust the movements, like smartphones. Yeah. Sir, it's in our day-to-day life, no, sir. How we can leave this out?
Smartphone app.
Myoware. She said Myoware.
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 Yes.
Yeah.
Yeah. Yes. Yes.
Myoware is operated like.
No, sir. It's an app.
Right. So that's what I'm saying. Smartphone app. That's right.
Yes.
Somebody else here came up with a similar idea. Okay, all right.
We can control prosthesis by digital twin based simulation integrate with artificial intelligence.
That's a job. Okay, all right. Digital twin. Let's give it up. This is idea.
We actually had two ideas. Okay.
anatomical coupling. On day one, you have explained about how you cannot move the ring finger without moving the middle finger. So similarly, every action in the body will have a residual signal in the other part of the body also. So if I'm moving my right leg front, I am going to stabilize my body based on the effort I'm going to put on the left leg. So if I'm not having only one limb, I can take the residual signal from the other limb and use it here. EMG signals or synapse signals, whatever it is. But EMG signals, mostly it will be EMG signals. Yes, sir. IMA based weight detection, sir. So.
Who's the spokesperson?
Sir, it is based upon the static instruction to process it, like haptic feedback. How to move, how to initiate means it is full of a mechanical and electric control over the prosthetic devices. It's yeah, okay. So it's a predefined function. How to use, how to move, how to learn. How it is one of the device, artificial device we fix the prosthetic. So yeah, we given us some feedback. What is okay through signals? So EMG only. EMG. Most preference is EMG, sir. Second preference is EEG. Yeah, haptic feedback. Okay, thank you
so much. Let's give it up. Okay.
So, multimodal approach, we're thinking about maybe tongue control, like tongue movement, and then head and neck movement and respiratory thing. Head and neck movement and breathing, like multimodal.
All the above. All right. What's the spokesperson? Sure.
Myoelectric control in the sense same senses we placed sense we can keep the sensors in the muscle tissues surface so that the electric signals when we get through the sensors we can have some support control the near the joint areas. Yeah, yes. Sensors. That also we can do. Yes.
Surface. Non-invasive, invasive, non-invasive EMG sensors. As long as I'm not. Yes. Not. Breathing we already got. Yeah, the multimodal guys, they draw like 7 answers.
Upper. So the upper lip implant, the contralateral upper lip. When we move this.
Contralateral, we also got that. Okay, fair. Thank you. Let's clap. And let's clap for the multimodal and the first team as well. Thank you. Thanks so much. Thank you so much. Thank you. So So looking at this, we have a lot of EEG candidates. 1, 2. Exactly when I said a lot of, I'm not able to find 3 non-invasive. No. This is not. That's different. Okay, so we have 3 EEG. We have 1, 2, 3, 4 EMG. Then we have multimodal. Multimodal we have. Right, so this is one invasive. So invasive, one invasive accelerometers, filter design, app is another smartphone app. So I think we got 2 of them, right? Okay. And then implanted, okay. And then nerve stuff was the other one. Okay. All right. How did you feel about that? Yeah. You all learned something from this exercise? Did you all learn something? Yes? Yeah? Okay. The time is 1:04. What's the lunch time? 1 o'clock. We already. The lunch is 1 to 2:30. So what should we do? Should we fast? And should we continue? Of course not. Okay, so let's take a lunch break and we'll come back after that. But great job, all of you. Thank you so much. Thank you. Brilliant answers. Thank you so much. All right.